And now a zero effort miss guidance example. Recall that zero effort miss was simply the miss distance that resulted if the pursuer and target continued along their present course without maneuver to some final time. This is illustrated here in our engagement diagram where the pursuer is off of the collision triangle by some heading error, and that results in a miss distance vector at TF. Because the pursuer and target are not maneuvering in this, that miss distance vector is also zero effort miss. And we derive the formula for that in the inertial coordinate system, but then represented zero effort miss in a line of sight coordinate system and took out the component perpendicular to the line of sight. And then we also determined the linearized form of zero effort miss perpendicular to the line of sight, which was greatly simplified. And here Z is the separation between the target and pursuer in the K direction. Time to go, of course, is TF minus the present time, T. Now we also saw that zero effort miss in the linearized form was proportional to the linearized line of sight rate. And that allowed us to make a substitution into the true proportional navigation law to come up with a zero effort miss form of true ProNav, where zero effort miss is proportional to the maneuver requirement of the pursuer. Now going back to a familiar scenario where the pursuer and target were initially on a head-on course, but the target accelerates, evading the pursuer. We've interpreted this scenario previously in this section in terms of line of sight rate and closing velocity, but now we want to interpret it with the new variable zero effort miss. So here's a plot of the zero effort miss versus time for both the linear and nonlinear engagement. The target is accelerating at 5 Gs throughout and the navigation gain is 3. So initially the pursuer and target are pointed straight at each other, and if they were to continue along that course, there would be no miss distance. And that's captured here in the zero effort miss chart where it starts off at 0. But because the target accelerates as time proceeds in the simulation, then there is some error to that collision course. And so as the target accelerates, more and more error is introduced, but at the same time, note that the ProNav is providing feedback to the pursuer and it begins to accelerate to correct that collision course. So ultimately, there is a maximum zero effort miss before the pursuer gains a handle on the engagement and regulates that zero effort miss back to 0 as the collision course is achieved and the time to intercept, or TF, is approached. In summary, zero effort miss is just a prediction of future miss distance starting from the current time and assuming that going forward the pursuer and target don't maneuver. They continue on their immediate headings. We saw that zero effort miss is also related to the pursuer maneuver necessary to establish a collision triangle. If zero effort miss is 0, no maneuver is needed. But if zero effort miss is large, then greater maneuver by the pursuer is needed to get on the collision triangle. The zero effort miss form of proportional navigation provided a proportional relationship between the predicted miss, that's the zero effort miss, and the pursuer maneuver requirement. Arguably, this is a more intuitive form of ProNav where large predicted miss means larger pursuer correction or larger pursuer acceleration, and vice versa. And this relationship was highlighted in the head-on engagement here. Initially, zero effort miss was 0. We were on a collision course, and then the target maneuvered, introducing predicted miss, but that was corrected by the ProNav and through the acceleration of the pursuer so that the pursuer regulated zero effort miss as time approached the final time. This was a zero effort miss guidance example in Missile Guidance Fundamentals, Section 4, Module 4.